A useful way to work with sets involves using something known as a Venn diagram. In a Venn diagram, a closed figure, typically a circle for convenience, represents a set. For example, in the Venn diagram shown, we have a circle, which is corresponding to our set A, which we've labeled, and X is inside the circle, so X is an element of the set A. Meanwhile, Y is outside the circle, so Y is not an element of A. The different regions of the Venn diagram translate into set expressions. So again, the region inside the circle corresponds to the set itself. The region outside the circle corresponds to everything that is not in the set, and so it corresponds to a complement. What if we have two sets, A and B? Now, if we don't know any information about the sets, we should draw a generic Venn diagram. For example, if we draw the Venn diagrams this way, it is impossible for any element to be in both sets. But we don't know that, so we don't want to draw it this way. If we draw the sets this way, then again, it's impossible for something to be in B, but not also at the same time be in A. And again, we can't guarantee that, so we don't want to draw the Venn diagram this way either. So our generic Venn diagram has to look like this. Now, given two sets A and B, we can express several different set relationships. For example, there's the set A itself, and notice this includes a region that's in B. Then there's a complement. And again, notice that this also includes a region that's in B. Next, there's A union B. This is everything in A together with everything in B. We also have A intersect B. And this is everything in A that is also in B. Now, part of the reason that Venn diagrams are useful is that a Venn diagram can be used to illustrate, but never prove, certain set relations. We'll start with the illustrations first. So a useful idea is that any problem in geometry can be simplified by using Scotch tape and scissors. We can join two regions together, or we can remove a region from another region. In set terms, joining all of one set to another set corresponds to the union of two sets. That's our Scotch tape. And to remove a region, that's a little bit more complicated, but imagine a set is like a cutter. Intersecting with a set removes everything that isn't in that set. For example, consider the shaded region shown. So to produce the region shown, we can start with everything outside of B. That corresponds to B complement. Then we can use the A cutter, that's the cookie cutter in the shape of the set A, to cut just the portion inside A. And so this is the region B complement intersect A. On the other hand, if we're given a set expression, we can identify which part of the Venn diagram we want. For example, complement A union complement B. Since this is a union, we're going to tape two things together. Complement A is everything outside of A. That would look like this. Complement B is everything outside of B. That would look like that. In a perfect world, we'd always get set problems expressed using intersections, unions, and complements. We don't live in that world. We might be given a set expression in natural language. For example, let R be the set of retired people and G the set of golfers. We can draw our generic Venn diagram. A person who is a retired golfer is retired, so they have to be somewhere in R. But they have to be in the part of R that's also in G. So they have to be in this intersection, R intersect G. But a golfer who is not retired is a golfer, so they're in G. However, they can't be in the part of G that's in R, so they need to be in G intersect R complement. And a person who is either retired or a non-golfer could be in R, or, since they're a non-golfer, they could be outside of G, so they're in R union G complement.